How GPS actually works. Why Einstein is inside your phone. You are standing in the middle of a strange city. You open your phone, look at the map, and see a blue dot blinking exactly where you are standing. It feels like your phone is reaching out to the sky, pinging a satellite, and asking, "Where am I?" That is the common intuition. But that is completely wrong. Your phone does not speak to the satellites. It only listens. And the satellites are not looking for you. They are simply shouting the time. Welcome to the hidden science of the global positioning system. The biggest myth about GPS is that it is a two-way communication system like the internet or a phone call. People imagine a beam of data going up and coming back down. In reality, your phone is surprisingly passive. The GPS system consists of a constellation of about 30 satellites orbiting 20,000 kilometers above the Earth. These satellites are essentially flying atomic clocks. They do one thing. They broadcast a signal that says, "I am satellite X, and the time is precisely Y." That is it. Your phone is just a receiver. It catches these signals from multiple satellites at once. And from this simple information, who sent the signal and what time it was sent, it calculates your position with meter-level accuracy. How does knowing the time tell you where you are? This brings us to the core mechanism, trilateration. Imagine you are lost in a dark forest. You hear a shout from the north. "I am 10 seconds away." You know sound travels at a certain speed. So, you can draw a circle around that voice with a radius of 10 seconds of distance. You are somewhere on that circle. Then you hear a voice from the east. "I am 15 seconds away." You draw a second circle. Now, there are only 2 points where those circles overlap. Finally, a third voice shouts from the west. When you draw that third circle, all 3 intersect at a single point. That point is you. GPS works exactly like this, but instead of sound, it uses radio waves traveling at the speed of light. The speed of light is roughly 300,000 kilometers per second. When a satellite sends a signal, your phone notes the time it arrived. It compares that to the time the signal was sent. The difference is the travel time. Multiply that time by the speed of light, and you get the distance to the satellite. Ideally, you need signals from at least 4 satellites to pinpoint your location in 3D space: latitude, longitude, and altitude. But here is where the physics gets incredibly complicated. To measure distance accurately using the speed of light, your timing must be perfect. Light travels 30 centimeters in 1 nanosecond. If the satellite's clock is off by just 1/millionth of a second, your location on the map would be off by 300 meters. You would miss your exit on the highway by 3 football fields. This requires atomic clocks on the satellites that are precise to the nanosecond. But even with perfect clocks, there is a bigger problem. Albert Einstein. The GPS system is the only everyday technology that relies on both special relativity and general relativity to function. Without Einstein's equations, GPS would break within minutes. Here is the deep dive. First, special relativity. The satellites are moving very fast, about 14,000 kilometers per hour relative to you on the ground. According to Einstein, time actually slows down for fast-moving objects. This means the satellite clocks tick slower than your phone's clock by about 7 microseconds per day. Second, general relativity. The satellites are far away from Earth's heavy mass. Gravity is weaker up there. According to Einstein, time moves faster in weaker gravity. This effect causes the satellite clocks to run faster than Earth clocks by about 45 microseconds per day. Do the math. They run 7 microseconds slow due to speed. They run 45 microseconds fast due to gravity. The net result is that satellite clocks run 38 microseconds faster than Earth clocks every single day. 38 microseconds might sound like nothing, but remember the speed of light. If we didn't correct for this, that timing error would accumulate into a location error of 11 kilometers per day. Your GPS would be useless before lunchtime. So, before the satellite even sends the signal, engineers have programmed the onboard computers to artificially slow down the atomic clocks to match the speed of time on Earth. Your Uber arrives on time because we accepted that time is relative. There is one more hurdle closer to the ground. We call it the urban canyon effect. This explains why your blue dot sometimes jumps around wildly in a city with skyscrapers. GPS signals are weak. They are like the light of a 20-watt bulb seen from 20,000 kilometers away. In a city, the signal doesn't always hit your phone directly. Sometimes, it bounces off a glass building first, then hits your phone. This creates a longer path. Your phone thinks the satellite is further away than it actually is. This is called multipath interference. The math gets confused because the radius of your circle is wrong and the intersection point drifts. This is why your navigation often spins in circles when you are surrounded by tall buildings. So, how do you use this technology more effectively? Here is the utility protocol for GPS. First, the DO protocol. DO enable Wi-Fi scanning or high-accuracy mode in cities. Since GPS struggles with multipath interference in cities, your phone uses a secondary trick. It knows the location of millions of Wi-Fi routers. By seeing which Wi-Fi networks are near you, it can triangulate your position roughly, correcting the drift from the satellite errors. This is called AGPS, Assisted GPS. It is essential for urban navigation. Second, the DON'T protocol. Don't rely on GPS altitude measurements for hiking safety. While GPS is great at latitude and longitude, horizontal, it is terrible at altitude, vertical. Because all the satellites are above you, the geometry is weak for calculating height. The vertical error margin is usually 3 times worse than horizontal. If you are hiking near a cliff or in a mountain pass, trust a physical map or a barometric altimeter over your phone's GPS elevation reading. Third, the WHEN protocol. When you see a large blue circle around your dot, wait. That circle represents the uncertainty radius. It means the phone hasn't locked onto enough satellites yet. It might only see 3 instead of 4. Moving while the circle is huge will only confuse the navigation algorithm further. Stand still for 10 seconds to allow the phone to download the ephemeris data, the map of where the satellites are supposed to be. Let the circle shrink before you start walking. In conclusion, GPS is a quiet miracle. It is a system that requires rockets, atomic physics, and the bending of space-time just to help you find the nearest coffee shop. We have built a constellation of artificial stars that speak to us in the language of time. The next time you follow that blue line on your screen, remember that you are navigating by the laws of Einstein. You are not just holding a phone. You are holding a device that proves, every single second, that time is relative.